I am Edeve Finkechi, and I'll be moderating today's class, and Emmanuel will be assisting me in doing that. Emmanuel, you're welcome.
Yeah, thank you.
And you're welcome, sir. So I missed us again. So we have like 12 participants currently. So I don't know if we can start the class, if that's okay by you, sir.
Okay, good evening, everybody.
Good evening, sir.
Yeah, I hope everyone can hear me loud and clear.
Yeah, we can hear you.
Yes, sir.
Okay, okay. So welcome to today's class. Last week we started our class on the seismic acquisition, and today we will continue. So can you see my screen?
Yes, sir, I can see it.
Yes, sir, we can see.
Okay. So last week we had our introduction on seismic acquisition, and here is the outline where we looked at the key steps in our seismic acquisition. Seismic characterization of good seismic data, characteristics of good seismic data rather, and we ended with a few classworks, which some of you have responded to, and we did well. So last week we briefly did introduction where we said normally the seismic acquisition is the first step, after which you process your seismic data and then interpret them, which are the last two steps. So which we know is basically the generation of artificial seismic waves that will reflect from on rock boundaries, what we call acoustic impedance construct boundaries, and come back to the surface and then being received. We looked at some key acquisition steps, which are survey design, spread configuration, deployment of receivers and source, navigation and positioning, shooting, timing, synchronization, and all that. So we started looking at a survey design. Some of these acquisition steps will be embedded into our discourse. And we looked at survey design, where we said for you to do your seismic acquisition, you have to know your objective of what you want to why you want to acquire the data, because there are different types of seismic acquisition. So your purpose determines which one you want to do. What is your target in terms of subsurface depth, resolution of the data you want, the environment you're working on, and the type of survey that you end up doing, and the equipment you use. And then you have to review whether you have data available and look at the available data already to compare with what you want to, as in use it as what we call a baseline. Sometimes you'll call it the baseline or your vintage that we use for your comparison and all that. Still on acquisition survey designs, we also looked at what's your purpose in terms of the environment. Are you on land? Are you in the marine setting? And all that. So on design, we looked at some acquisition parameters. While you're trying to define your purpose of doing the job, you have to know come up with acquisition parameters, being size, source line spacing, receiver line spacing, and all that. And your fold, your offsets, maximum, minimum, and all that. So record length and sampling rate and all that. Then we looked at spread configuration, Do you want to use a split spread or single-ended spread for the acquisition? Split spread where your sources are in between receivers, or where your source is at one end of your receiver lines. Then we looked at configuration, where I tried to explain using the Niger Delta Basin. In terms of your geographic coordinates, north, south, east, and west, what is the orientation you're going to put your acquisition? Are you going to run them on the northern direction? And these are dependent on your decision on the orientation is dependent on the structure you are, the subsurface target structures. Are you targeting that? You have to know the geology of the basin you're working in. So I use the Niger Delta Basin for illustration. We have the growth faults in the Niger Delta. We know the orientation of the growth fault in terms of their dips and their strikes. So your acquisition lines will have to go perpendicular to the strike line of your structure. That's if you have predominance of faults within the basin. So it has to be perpendicular to them so that on your inlines you can see your faults when you're interpreting the seismic data. Because if you put your inlines in on the same direction with the strike, when you want to do interpretation, it will be difficult to pick out your faults. So we looked at characteristics of the good seismic data, which we say it has to have a good signal to noise ratio, good temporal and spatial resolution, and a good spatial coverage. And for you to do a successful seismic acquisition, you have to put cost in your cost effectiveness in your plan. Consider the health HSE standards and work within a scheduled period. So you don't have to overshoot your time plan and all that. And I also threw light on what signal to noise ratio means, where you have to have what signals are, which are the reflections that your seismic waves are picking, your seismic recorders are picking rather. When you have your seismic wave traveling and reflecting at rock time boundaries, so the waves that are reflecting due to acoustic impedance contrast, they are the reflected seismic waves and they are the signals. Any other thing that your recorders are picking up, they are noise, and all of them will be measured or recorded within your seismograph. And you're interested in the signals. So your signals you have to have more signals than noise in your data. So if you have more signals than noise, then you have good signal to noise ratio or high signal to noise ratio. But a situation where there are more noise in the data than signals, then your signal to noise ratio is very poor or low. So it's not ideal or acceptable. So you need to aim for higher signal to noise ratio. Then when we talk about spatial coverage, depending on your target structure and its depth, you need to have an offset. I explained offsets, the surface distance covered by your acquisition configuration. So you have to have a high offset to cover, depending on the target's subsurface target depth. And then the density of the acquisition in terms of a number of receivers you have over a period where we try to calculate for this. And we calculated about 150 based on 50 meter interval for four receivers. And when we have 8 receivers, meaning higher density, how we can have better imaging of the structure. And when we have higher density of more up to 12 to 16 receivers, we'll be able to view our structures better and all that. So these were the things we touched last time. Looking at uh, uh, acquisition density and the spatial coverage. Then we looked at temporal resolution, where I explained that frequency plays a very key role in the resolution of your seismic data. The higher the frequency, the higher the resolution. The lower the frequency, the lower the resolution of your data, because the higher frequencies will image more of your subsurface geology, while the lower frequency will image less of your subsurface geology. And and you need both the high and the low frequencies. Because low frequencies travel far, they do not attenuate easily, so they image deeper, even though the resolution may be poor at depth. But your higher resolutions image they don't higher resolutions attenuate faster rather. The higher frequencies attenuate faster, but they do not travel far, while your lower frequencies take more longer time to attenuate, but they travel deeper and image deeper in the subsurface, but with lower resolution. I try to use this diagram or this image to show the effects where you have on the left a seismic data with a lower frequency broadband, where the dominant frequency is between 7 and 33. And the second image on the right, where your frequency spectrum is showing you that the frequency spectrum is between having a dominant frequency between 1.6 Hz to 53. So when comparing, you find that even though they are both seismic data are the same, the resolutions are not the same. The one on the right has a better resolution than the one on the left. But structurally wise and every other thing, they look exactly alike. But when you look at it deeper, critically, find out that the one on the right gives you subtle, better imaging than the one on the left. And we ended the other class by looking at some classwork where we try to calculate dominant and apparent frequencies from our seismic data. And I gave some classworks that we attended to. So today, I want us to look at some terms before we go into the acquisition methodologies or equipment and all that. Remember last time we talked about, let me bring this here. Last time we talked about, just hold on 1 minute. We talked about the acquisition parameters. Yeah, I tried to explain them in terms of the line spacing and all that. So I felt I didn't throw enough light on that, so I added 1 or 2 slides to explain better. When we talk about receiver lines and source lines, so you can see from this diagram, the image here. I'm sure you can still see my slides properly, right? There are no lags.
Yes, sir.
Okay, so for instance, the diagram you have here, you have the red dots represent your sources, and your blue boxes represent your receivers. And you remember that we said you need to have your source line spacing, receiver line spacing. These are questions you answer when you're designing your survey, your station intervals and all that. Number of receiver per station and nominal folds and all that. So for us, when you come to the blue line, let me use a pen. The blue boxes represent receivers, for instance. And as it stands, this will be your receiver line 1, this line. Okay. So this will be a typical receiver line 1. This line, with all these receivers on it, will be your receiver line 1. And this one will be line 2 and line 3. So while you're choosing your survey design, where you say your receiver line interval, it means the distance between this receiver line and the next receiver line. That's your receiver line interval. And these are the things that play a key role when we talk about survey density. So in one survey, the receiver line interval is 500 meters, for instance. And another survey, receiver line interval is 250 meters. So it means that the survey densities will be different. Also, the receiver line, as we have them, when you saw cut off each receiver, what is the distance between each receiver, which we treated last time? These are things that play a key role. Also, your short line, your short lines. These are your short lines. I need a red pen. These are your short lines, the one that runs perpendicular to the receiver line. And so the interval between the short lines also matters. So what do they decide to be? Sometimes they make a grid that is uniform. So if your receiver line is 500 meters, your short line will also be 500 meters apart. Okay, and receiver intervals will also be the same as your short intervals, the positioning of the shots. Their interval will also be the same with the receiver lines and all that. So these are things you need to know when you come of survey designing. So if you're in a place and they're talking about the acquisition of seismic data and they're talking about receiver line, source line, and all that, this is exactly what they mean. Remember, my aim in here is to make you understand the basics about seismic acquisition, processing, and interpretation, so that wherever you get to, you will not have any fear. When they are talking, you understand what they are talking about. You may not yet be an expert at an entry level, but you will not be a novice. That is my primary objective in these mentorship sessions. So, so that is what it means. Then you also have what we call SWOTs. This is what we call a SWOT. So during acquisition, you have this. This is the second image on the right is also like the first one, but you can see that there's what they call SWOTs. So in the sense that you can pick up, let's say from receiver line, this is receiver line 1, 2, 3, 4 to maybe N. You now use the receiver line 1 to maybe 1 to 6. Okay, 1 to 6, and you run the acquisition on receiver line 1 to 6. So from 1 to receiver line 1 to line 6 becomes a SWOT. You call it SWOT 1. Okay, SW1. When you finish acquiring within this area where you have receiver on 1, so you want to now continue acquiring on the other side where you now have from receiver line 6 to another line here, 7, 8 down to whatever. So from there, receiver line 6 stops here. Okay, so your SWOT 1 is from here to line 6. That's your SWOT 1. So the next SWOT, you overlap. They will do an overlap. They will not start from SWOT 7, which is 7, 8, 9, and 10, and continuously. They will not just start from 7. They will overlap it with 6. So receiver 5, line 5 in SWOT 1 will become line 1 in SWOT 2. And then, so your SWOT 2. So there will be an overlap. I don't know if you get what I mean by overlap. So what was the last SWOT? Line 6 here was the last SWOT for SWOT 1. This will now be SWOT 2. And that SWOT 2 will start from where line 1 was, so that there will be an overlap. Okay. And that is what you see on the image on the right, where you have SWOT 1. You see SWOT 1 here. And then you have SWOT 2. You can see SWOT 2. Even this one, they have more than one line as overlap. SWOT 3 and all that and all that. So why do they do swatting? If you have an oil block like this, if you have an oil block, let's say OML, what do I use now? OML 20 or OML 30 or OML 100, whatever. Anybody know what an OML is? Can I get a response? What's an OML?
Oil mining leads.
Okay, what of OPL?
Oil prospecting leads.
Okay, that's good. So if your company is having an OML or an OPL, whatever, it's just an oil block that the nation or we are operating in has divided their oil region or their petroleum region, like the Niger Delta region. They divide them into blocks. And so they gave you one block. One block may be very large in size. Let's say your block is covering the whole of Port Harcourt region. So you can know that that block is having a very large in size. The block is very large in size, maybe 100 kilometer by 100 kilometer in size. Okay, that means the size of the block is 1,000 square kilometers. Abi? So this is the size of this oil block, for instance, 1,000 square kilometers, because it's 100 by 100, for instance. No oil company, no contracting seismic acquisition company will run a receiver line that is 100 kilometers long. Your receiver lines may be one receiver line like this from the beginning to the end, maybe like 10 kilometers in length. And you know, this is more than you have 100 kilometers. So that means receiver lines, let me use a red pen. So your receiver line 1 will be from here to maybe here. Line 2 from here to here. Line 3, 4, 5, and 6. So this is your SWAT 1. Okay? So SWAT 1 within this block is just this region that you have your red line. And that's where they're going to shoot. But the company wants to cover seismic acquisition in the whole of this block. So SWAT 1 is from here to here. The acquisition company has done SWAT 1. They will now overlap SWAT 1 and 2. They will now do SWAT 2 from here. This is SWAT 2. And then they will do SWAT 3. Here's my pen. Hold on. And then they will do SWAT 3. Let me get a black pen. So you have a SWAT 3, maybe overlapping SWAT 2 and all that. So this is why what we call swatting in seismic acquisition. So where you have the red lines, that's your SWAT 1, your red receiver lines. The blue one is your SWAT 2. The black ones are your SWAT 3. So they will repeat it. So you have SWAT 1, 2, and 3. So when they finish acquiring SWAT 1, they will move to SWAT 2. What they are doing is that they are dividing the oil block into small batches, okay, and acquiring them small. So they will repeat the things. Maybe this one now SWAT 4, SWAT 5, SWAT 6, SWAT 7, SWAT 8, and SWAT 9. So they will divide the block into small SWATs and then cover it gradually by gradually. Maybe in the month of January, they will cover SWAT 1. And ending of January, they cover SWAT 2. February, SWAT 3, and all that until maybe 6 months to 1 year, depending on the size of the area and all that. So that is what these receiver lines and the SWATs means. So I decided to throw more light on that based on what we discussed here last time. Then I also like to point out back to this. Is there any question before I proceed? Then is there any confusion? Do you understand me?
Yes, we do.
Okay. So when you're in a
Sir,
place and
I have a question, sir.
yes, that's
Please, sir, the swatting, is it only along the receiver line?
no.
Okay.
I'm using receiver lines for just as you put your receiver lines, you put your short lines perpendicular to it now.
Okay, sir.
You acquire. So when they are in SWAT 1, they will do everything complete. Put receiver line, put short lines, and acquire. Put their shorts and acquire. So what it means is that they will do everything acquisition on SWAT 1
Okay.
and record the data and collect the data and archive the data, whether they archive or they send it for processing, whatever. Then they'll go back and they'll continue and do SWAT 2. The essence is to break this oil block that is 1,000 square kilometers into small portions. You can't acquire all of them in one day. In one go. So you break them down into small portions, and those portions have to overlap themselves. And those portions are called SWATs. So when you're in an environment and they're talking about they will acquire SWAT 1. So you just have to know that they broke down their oil block, they shared it into a smaller bit, and acquired, okay? And acquired it small, because the block is big. You can't run receiver line. Let's say one oil block is as big as, I don't know, a town that all of us are conversant with. Most of us know the whole of Lagos. You've been to NAPE conference, and let's say one oil block is as big as Victoria Island. You can't run a receiver. They may not want to run a receiver line, or they may not even have receiver lines that is very as long as covering the whole of Victoria Island in one go. So they will break it down into short lines. Okay. When they finish one region, they transfer to the next region and all that. That's why they not call any small region they acquire is a SWAT. So that is what SWAT means. So they will acquire SWAT by SWAT. So if you hear the word SWAT, that's what it means. It's just like in your house, you want to tile your room. Do they bring one big tile that covers the whole floor? No, they put the tiles small pieces by small pieces until you cover the whole floor. So each of the small piece of tile that you buy, they install like 60 by 60 tile. That's a SWAT. And you put the next one. So that's what a SWAT means. So the next thing I want to bring is a CMP and CDP. Okay. Remember we talked about when we were talking about seismic method, I told you it stems from the Snell's law, where for instance, your receiver one, your source one and receiver one, when the seismic wave travel from source one to this to an interface in the subsurface, it reflects back to receiver one. Okay, so the angle of incidence and the angle of reflection are going to be equal. Okay, the point where that reflection occurs, okay, is known as your common midpoint, your CMP. Your what? Common midpoint. The point where it occurs in the depth is your common depth point rather. While your CMP is the distance between the mid of the distance between the source and the receiver. So if the source is here and the receiver is here, the distance between them, let's say, is 100 meters. Your CMP, or is the common midpoint between the source and the receiver, will be 50 meters. Okay? And that 50 meters interval will correspond vertically to a reflecting subsurface point in the subsurface. And that point will be your common depth point where the reflection occurred. Okay? Now, when you increase the offset away from where you have receiver one, so you have your source 2 and receiver 2. Both of them, based on angle of incidence and angle of reflection, both of them will also have this common depth point, but their CMP will be different because the distance from this receiver to this source have increased. This one was 100. Even if the distance have increased to, let's say, 200 meters apart, so the CMP between them becomes the 100 points, meaning you divide this by 2. So the midpoint between them is the CMP. So I believe you understand what I mean by that. So you have to know what we call CMP, and the point in the subsurface where the reflection occurs is a CDP. So depending on the position of different receivers and source, a point in the subsurface can be a CMP to multiple receivers and multiple sources. Does that make sense to us? If you look at it in a 3-dimensional view, a common midpoint can serve for different receivers and different sources, depending on their offsets apart. Is there any confusion? So with the absence of that, so when you have a CDP, this CDP can serve for multiple receivers and multiple sources. What it means, ideally, is that this particular point in the subsurface has been imaged 3 times by different sources and different receivers. Remember, during acquisition, they don't shoot all the sources simultaneously. You have your receivers already placed, 1, 2, 3. When you shoot for source 1, this one, the receiver that picked up based on the location of this source is this receiver 1. When you now shoot for source 2, the receiver that picked up based on angle of incident and reflection is receiver 2. And when you shoot for a shot 3 or source 3, the receiver that picked is receiver 3. But what is common is that all of them reflected on this particular CDP. All of them are reflecting from this point. What it means is that this point in the subsurface has been imaged 3 times by different receivers, receiving information sent from 3 different sources. So these 3 places has been imaged. This particular point has been imaged 3 times. And that is in this cartoon now, the fold of this image or this diagram is 3-fold, nominal fold. Remember, one of the parameters of interest is your nominal fold. When I talk about nominal fold of your data. So when you hear nominal fold, they tell you what is the nominal fold of a seismic data. It means most times a typical seismic data, they will be seen nominal fold, 50-fold, 100, 50-fold, 100-fold, 40-fold, 60-fold. The higher the number of folds, the higher it means that the higher the number of times a particular point was imaged or was, a particular point served as a CDP. So if this point in the subsurface served as a CDP to 50 different receivers, up to 50 different receivers, it means that the fold of this data in terms of this point is 50-fold, because 50 sources and 50 receivers, we are able to image. We are looking at a seismic ray path here, is imaging this particular point. So that is what fold is. So that brings us to the idea of binning. I'll still go back to fold again. That brings us to the idea of binning. You have your receiver lines, you have your short lines. They will give you a grid, receiver, source, and short. Receiver line and source line has generated what? A grid. So the gap between them becomes a grid. And that gap can be further divided into smaller other points or grids. And these smaller grids is known as your bin. So in your seismic data, you have a bin, what we call the seismic bin. So it's kind of used to spatially organize your seismic data, because during processing, it is this seismic bins that helps the processing the processor to sort the seismic data into CMPs and CDPs. Now, your seismic bin, one bin like this will have a common midpoint in the middle. Okay, meaning within these points, how many receivers and sources image these points within these small bin grids. Okay, how many receivers and sources image these points? So the higher the number of receivers and sources, as explained earlier, that image these points, the higher the number, that determines the number of the fold of your seismic data. So it's like you going to a studio. I don't know if you see that, when they are doing a movie clip, movie production, you see them, they use multiple cameras. Why are they doing that? They are capturing the image of the production of the film or whatever from different angles. One camera is in front of the actor, another is by the side, another is by the left and the right side, another camera is behind him from every angle, and another camera is above him, and other they even put one under if it's possible. Why? They want to see the actor from different angles. So in seismic acquisition, binning helps you organize your seismic reflections based on multiple receivers and sources that image this point from different angles. As the spread is changing or increasing, or the offset is increasing, the receiving angles of your seismic data is also increasing and changing. So multiple receivers and sources from different offsets are going to be imaging these points. Okay, so the number of those receivers and sources gives you the fold. And you get your bin by this simple formula: source interval over 2 times receiver interval over 2. So no matter what the source interval is. So if we say the source interval here is 500 meters, and the receiver interval here is 500 meters, and the source interval between them is also 500 meters. So what would be the bin of the seismic data here? So somebody quickly tell me the bin size.
500.
The bin size will be 500, right?
No.
500, sir.
Is it 500? It's more than 500.
It's more than 500.
Yes.
Okay. It will be more than 500. That's your natural bin. So within the bin, 2,500. That is quite large. So
Let me see. 500. 1, 2, 3, 4. 1, 2, 3.
You're correct. It's 2005 because sorry, when you divide 500 by 2, you get 250. 250 times 250. So that gives you your bin size. So you remember we're talking about survey density. So another survey where the receiver interval is 200 meters apart. Okay, and the short intervals are maybe 100 meters apart. Your bin will also be different from what this bin is. And if that happens, it means this, because the idea is to have a smaller bin size. The smaller the number of your bin size, it increases the resolution of your data. So the next I'll look at here is the fold, your nominal fold of your seismic data. I tried to explain that based on binning before and your CMPs. So this is your bin. Remember that one seismic, your receiver gives you a seismic trace. Remember what we did before. So within this bin, for instance, let me use this image for example. So within this bin here, okay, when you get, first you have your natural bin, and then your natural bin is further divided up or further shared down into smaller, into your final bin size. So this is your bin. Okay. Now, how many reflections, okay, occurred within the subsurface on this bin on a particular rock interface or geologic interface? So what it means is that on this bin, receiver one, this is receiver one, and based on CMP, this bin is at the common midpoint between this receiver one here. Let me use green pen. So this receiver one here, this bin is a common midpoint between this receiver here and this short here, this source point here. Okay, so this is the bin. This is the CMP on this bin. Another receiver, if we have another receiver here, for instance, receiver 2, here, this is a receiver 2. Where would the source that will form a CMP with this bin be? The source will be somewhere here at the far offsets here. Okay, so you have another source here, source 2, that will serve a CMP here. That will have this bin as its CMP. And so for this, you also have, if another receiver that is close to this bin, like this one here, this receiver has a CMP. This bin is serving as a CMP between this receiver and this source here. So this is how it is throughout the survey. So each bin, it doesn't matter where the bin is located, will serve as a common midpoint between corresponding receivers and sources, which will serve as a common midpoint between receivers and sources, depending on their offsets. Okay, so depending on the offset of the receiver and the source. So the total number of receivers and sources that uses this place as their CMP. So if you now have this bin serving up to 5 receivers or 10 receivers or 50 receivers, that gives you the nominal fold of the data. So here for this illustration, we have this bin in the middle on the left, serving as a CMP for 5 receivers. Okay, serving as a CMP for 5 receivers and shorts. So the fold of this data is 5 folds. Okay, So in another situation where you have the bin serving as a CMP, common midpoint, for up to 10 receivers and sources, you now have the fold to be 10 folds. So the idea is that during acquisition, your fold will be very high. So the bin will be imaged. Each of these small grid, which is your bin, will be imaged by multiple receivers and multiple sources. So it's like you being uh, uh, captured by different cameras from different angles. When let's say somebody enters a compound and there are up to 50 or 10 cameras in that compound looking at you from different angles. They will see you from every direction, your front, your back, your side. I remember when we are doing this illustration where when we are doing this illustration of seismic density, where we said when your density is low, you are imaging this image structure on one side. But when your density is higher, meaning you have more receivers and source, you will do what? You look at this structure from all angles, both on the right and on the left. So that is what your fold actually tries to tells you, that if you divide these into small bins, the larger the number of receivers and sources that views this point on the subsurface from different angles, the higher the number of fold of your seismic data. And then that means the survey density is higher. And the image quality will also be what? Higher, and your resolution will also, in other words, be higher if all other factors are put into good considerations. That's what all these explanations is all about. I don't know if we have any questions before we proceed. Okay. In the absence of that, we'll proceed to what we should be. Okay, so back to fold. At the end of the day, you have a fold diagram like this on the one on the right, meaning what this fold diagram or fold map means is that within the survey area, the middle part of the survey will have a higher fold coverage. You see the scale on the right. You see the scale on the right now. The part that is colored red has a higher fold of 40 folds, while the far part of the block is having lower fold, which is in blue to maybe about 10 fold. So when they acquire seismic data, the center of the data sets have a higher nominal fold, meaning the bins here were imaged by multiple receivers. That means for this part, for it to be read, it means that you have up to 40 receivers and 40 shots imaging each of these small bins. Okay, imaging these small bins. And that means the fold of the data is 40-fold. Maximum fold of this data is 40-fold. It's very important when they are talking about seismic data during acquisition and processing, because it will help in knowing that your seismic data is going to have at least good resolution. If somebody brings a seismic data that has 20-fold, they ask you what's the fold of the data, and they say it's 20-fold. Everybody will just say, the signal to noise ratio will be higher. And to have low signal to noise ratio, meaning there will be a lot of noise in the data. Processing the data will kind of be tedious. You have so many noise to battle with, especially by background noise and all that. But when the fold of the data is higher, 40-fold, 50-fold, it means that each of these bin was imaged by up to 40 receivers per time during the acquisition. And so the nominal fold is 40, maybe 50 and all that. So the higher the number, the higher the resolution of your data. And we expect to have a higher signal to noise ratio, meaning you have more signals and less noise in the data. And that is majorly ideally what we expect. And then in terms of offset, they also have what we call offset map during in the seismic acquisition process. In the offset map, for instance, if this is a short point, as shown in the cartoon on the left, the part I'm coloring green, all the receivers that are close to it, maybe receivers that are maybe 50, 100 meters or 200 meters away from this short point. These are what we call the minimum offsets, okay, or your close offsets. And then the receivers that are far away from these points or this short point here, or this point I colored green, receivers that are very far away from it, these are your far offsets, okay? So your far offsets. So, and then your near offsets, we have your near offsets, far offsets, you have your minimum offsets, you have your maximum offsets in your acquisition. Maximum offset means the maximum length of your receiver line, while the minimum offset is the minimum length of your receiver line, which is usually the distance between two receivers. Okay. And then near offsets are receivers that are close to a particular point of interest. Like you see the points colored green, and then the receivers that are near to it by the ones on light blue color. While your mid offsets, this is near, this is mid, and this is far offset. So these are also things we will put into consideration because as the offset is increasing, the angle of incidence and the reflection are also what's increasing. And these are things that we want to know, especially if you want to use the seismic data during interpretation for attribute analysis like the AVU and all that. So the offsets angles are important, and there's what we call stacking, near offset stack and mid offset and far offset stacks. So these are the or some parameters that you put into consideration during acquisition that will help the processor and the interpreter in decision making and all that. So having concluded this, today we are going to go further down and look at the seismic acquisition environment. Do I have any question before we proceed? So, any questions? So in the absence of any, so we're looking at seismic acquisition environments. I hope there's no lag in my slides. Are you seeing the current slides?
Yes,
Yes, sir.
sir.
Okay. Okay. So when you talk about seismic acquisition, everything we have been talking so far can be done on any of the acquisition environment, whether you're acquiring on land, you're acquiring on the marine setting or offshore setting environment, or offshore environment, or you're acquiring in the transition zone or the shallow waters, you do the survey design there. Everything you're doing is relatively about the same thing. Your binning, your fold, all of them means the same thing, irrespective of the environment that you're operating in. So for seismic acquisition, seismic can be acquired anywhere. Okay. So the image on the left is a map view. This is, let's say, land, transition zone, and deep water, or the marine seismic environment. So an oil block can be, let's say, like this. They give you a block like this. Another person has a block like this. Another company has a block like this. Another one has a block like this. And so on and so forth. Another one has a block like this. So depending on where your oil block is, your oil block can be on land. Let's say this is oil block 1, block 2, block 3, block 4, 5, 6, 7, 8, and all that. This one could be 9 and all that and all that. So what it means is, irrespective of where you are, irrespective of where the company you're operating have their assets, their oil block, where they are operating, you can do seismic acquisition. Whether the company is operating at OML1 or OML2 or OML3, or OML9, or OML10, it doesn't matter where the OML is. It could be land, it could be marine, could be on transition zone. You can acquire seismic data, and your seismic acquisition decisions and planning in terms of your survey, design, orientation, and everything. Does not have anything to do with whether it's land or marine. You design your acquisition the way you want it, the density, you're interested in resolution and all that. Where environment comes in now is when you're in the offshore environment, the equipment will change. Okay, what type of equipment am I going to use? If I'm on land, what type of equipment am I going to use in terms of your receivers and your source? So as you can see on this cartoon on the right, this is like taking a cross section of this is like taking a cross section here, a cross section AA on this our map view. Okay, so if you take this cross section, so this part is your land part of the acquisition. This is your land part. This is your transition zone to shallow marine, and this is your offshore and deep side marine sections. So wherever you are, the decision depends on the environment, on what to use in terms of equipment. And that is where the second part we are going into now, to look at different acquisition based on the different environments. So for the land acquisition, on land seismic acquisition, it can be done in swampy regions, can be done on mountainous terrains, can be done in the desert, can be done in the jungles and in the forests. As long as you're on land, it doesn't matter. You can acquire seismic data anywhere you are. Okay, or you just have to factor in some environmental concerns and then acquire the seismic data, be it land, swamp. You can see the image here. You have the one on the swamp. You see the kind of equipment they are using, a kind of a swamp truck or a swamp buggy, and all that. So we'll look at that in detail later. So for you, if you're on land and you're acquiring seismic data on land, which type of seismic source are you going to use? For the land seismic acquisition, we use the dynamite as one of the sources. Okay. In land acquisition, dynamite are used in areas where you cannot use your vibro size. There are areas you cannot use vibro size equipment. You have to use your dynamite. And to use your dynamite, you have to drill what we call a short hole. So this man mounting on this yellow painted equipment is drilling a well, like you're drilling a borehole. Okay, like you drill borehole. I'm sure all of us know what is borehole. So when they are doing land acquisition, they drill what they call short holes. Let me get a red pen. They drill what they call short holes. So if this is the earth surface where you are, like you have your houses here, for instance, you don't just drop the dynamite on the ground like this and shoot and explode it. Okay, then you have to drill a hole some meters into the ground, like you're drilling a well, a small borehole, and then put the dynamite at the bottom of the hole and detonate it. Okay, so the short hole could be what we call short holes, 30 meters to maybe 5 to 30 meters. So it depends. When we talk about processing, we'll throw more light on why you drill the short hole or the short hole. But just know that during acquisition, you drill what they call short holes and then put in the dynamite at the bottom of the hole and shoot. Okay, one of the reasons is that you need to have good coupling. Remember in your village, when you're doing your Christmas period, you shoot your knockout, pa, 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 you just drop it on the ground. The knockout will be blowing and scattering everywhere. But when you put the dynamite deep down into this hole, the energy that is generated by the dynamite when it explodes, acquisition, you need to generate artificial seismic wave. The energy is confined within this hole. So the energy propagates into the subsurface, okay, properly. So there's what we call good coupling of the energy when you are detonating your seismic wave or your dynamite rather, or generating the seismic wave. That's why one of the reasons why you drill the short hole. For this is one of the acquisition reasons. So I'll tell you these other reasons when we talk about statics correction and processing, maybe by next week. So let's leave this at this for today. So the advantage of the dynamite is that it can be used almost everywhere on land. Every terrain, you can use the dynamite to do acquisition, but it can be quite expensive. You know, if during acquisition, remember this diagram that we showed here now. You see the number of short points we have. The short point is the red points. You can see there are so many. So if during acquisition you have up to 1,000 shots, it means you are going to buy 1,000 pieces of dynamite. Okay? If you are going to have 2,000 shots, 5,000 shots, mind you, during acquiring seismic data, they are going to shoot the dynamite, or they are going to generate the seismic wave multiple times. So they are going to have up to 10,000 shots, depending on the survey area, the size of the survey area and the survey density. So some surveys have up to 10,000 shots and all that. It means you're going to buy 10,000 pieces of dynamite. They are not just like your normal knockouts you buy 200 though. They are more expensive and bigger. Like shown in this video, or this picture, they are quite bigger and more expensive. So it's labor intensive and expensive to use them. Labor intensive is that if you have 10,000 short points, you're going to drill 10,000 short holes across the survey area and then put the dynamite in each of the short holes. So somebody is going to be charging you to be doing this work this man is doing to drill the short holes. So even though the short holes are not very deep like your borehole, it's going to cost the company money to drill short holes, put in your dynamite and shoot. So it's capital intensive. It is labor intensive. It's time consuming. When you're using dynamite, if you have to shoot 1,000 shots per SWAT, you know what a SWAT is. So you're going to buy 1,000 dynamite, drill 1,000 short holes, and it's going to take you a lot of time to do all of them. And then there are safety concerns and safety concerns. You know, this is explosives. Handling of these explosives, you have to get an expert. The company have to have an explosive expert to be managing the dynamite warehouse, dynamite storeroom. It's not everybody can work there or go and work there, and you need some special government permits to even access your dynamite before they will say you are using it for terrorism and all that. So it has a lot of permit and safety concerns around it. Then there are environmental issues. You know, it's an explosion. It's an explosive. When you're using dynamite during acquisition, if it's in a country where environmental activists are very active, you come and start protesting and all that. You are disrupting the ecosystem. You are sending wildlife away. Yeah, when you shoot your dynamite, all the birds are running up and down. All the wildlife are scared and all that. So these are some of the environmental issues. And imagine drilling 1,000 short holes within a community or within a region. So these are small environmental concerns that surrounds the use of dynamite. Then the next type of source that you use for land acquisition is your vibro-size. So the vibro-size is a truck that is mounted with a plate that vibrates the ground and generates a seismic wave. So the good thing about the vibro-size is that for the dynamite, when you shoot the dynamite, you depend on the weight, the amount of energy that the dynamite generates. So when selecting dynamite for acquisition, they choose the size of the dynamite or the weight of the dynamite based on, they don't use the dynamite like small, like the knockout you use for Christmas. So it's a bigger, and they have different sizes based on the amount of explosion you want. But the vibro size machine can generate any amount of seismic energy you want, depending on how you tune the equipment to operate. You can generate any amount of any desired range of seismic frequency that you desire. So that's it. And for it, it's less expensive. Why is it less expensive than the dynamite? It can be expensive to purchase a vibro size truck, But at the long run, because it's one truck, it can cover large distances in one day without you having to. So the labor intensity is lower. You don't need to employ a shooting crew that will be drilling short hole, putting dynamite and doing that, and getting an explosive expert and all that. You just need a truck driver, a technician that operates the machine, and two other assistants, and they will drive this vibro-sized truck to the different short points. And then when they stop there, they deploy the vibro-sized equipment. Uh, this part is where the equipment, when they put this down on the ground, this is the coupling, the vibro-sized plate. They drop it down to touch the ground, and then they will generate the wave. So you can use it to cover large areas within a short period of time, and it has less environmental concerns because you're not going to disrupt the ecosystem while using the vibro-sized truck. But the only major limitation with the vibro-sized equipment is that it's not everywhere this truck can travel to. So if you have a swampy region, this truck can't drive into the swampy region. They normally use it in deserts, desert terrains, regions with relatively flat topography. Where you have mountainous regions, these trucks will not also work because they can't drive them and place them in a very steep hilly regions and all that. So this is its own limitation, but cost-wise, it's more cost-effective because after using the vibro-sized truck for one project, you can use it for another project and another project. So for 5-10 years, this machine is serving the company. But the dynamite is a one-time use. It's like a disposable. You buy, you throw it away. You use it once and you have to buy another one. So at the long run, dynamites are more expensive. So what are the receivers that we use for acquisition? There are different receivers for seismic acquisition that you place on your receiver lines, as we discussed what receiver lines are. So the receivers, the purpose of the receivers is that they measure the ground motion. As the ground is vibrating, the seismic wave is returning and there will be vibrations by the seismic wave. These receivers will pick the vibrations and transmit them into electric current or electric pulses, which is then transferred into your seismograph and produced as what we have as our seismic traces. You transfer from mechanical motions of the ground into electrical currents, which is then transferred to the seismographs as your seismic traces or seismic pulses. So the very common type of receiver is the geophone. We all know the geophone. Everybody heard of the geophone. So these pictures typically show you what a geophone looks like. So you can see this is one geophone. So the geophone has a spike, this leg, this iron spike, and they will pin into the ground. And inside this yellow casing of the geophone, you have a magnet and a coil. So when there's a ground motion, there's a vibration of the ground motion. The coil has a spring. This part is the spring. Because there is a vibration, the spring will be dangling, okay? Because there's a vibration of the earth surface or the ground due to the seismic wave that is returning, there will be a dangling of this the spring within the geophone. And while this spring is dangling around a static magnet, remember your electricity in basic physics. You generate electricity between when you have a magnet and a set of coil or wire rotating around the magnet. Okay, what happens? Electricity is generated. That's what is inside your electric motors in your generator or your whatever electric equipment you have. So the same thing happens within the geophone. So when you see a geophone, it's just magnet and coil inside. So when there is a vibration of the earth surface or due to seismic wave, the coil will vibrate due to the spring on it and generate electric current. And those electric currents corresponds to impulses, because the higher remember your reflection coefficient, the higher the reflection coefficient, the higher the returning seismic wave in terms of the amplitude. So the vibration will be higher. But when the reflection coefficient is low, the vibration will be small. And so the electric current generated will also be small. So this is how you now transmit it from mechanical to electrical and then back to your seismograph, which will now digitally record the information. Okay, so this is what how a geophone actually functions. And then geophones are connected one to the other through a cable. Okay, so this is typically a geophone, and this is a group of geophones, each of them having their cables. So during acquisition, they will put the geophones and then connect them. If you have your receiver interval, you have your receiver 1 here, your receiver 2 is here. It means one geophone is here, another geophone is on 2, another geophone is on 3, and each of them will be connected by these cables. You can see the cables now. There are different designs of geophone. That's what the second image is showing. Don't get confused. See this one that is bigger, that is looking like a small pot. Don't get confused. It's still a geophone. This one is still a geophone. This one is all of them are geophones. They have different designs depending on the company that developed the geophone. But the most common design is these spike geophones. Okay, and it can be tedious to install them over a large area and all that along your receiver lines. The next part of a type of receiver is the wireless nodes. This one is getting a publicity or popularity in recent time. Some of you on LinkedIn, you may have come across this company called Stride. Stride. They are very popular. You can Google them or you can check them out on LinkedIn. It's an acquisition company. The nodes are wireless geophones. They are just your geophones, but they are wireless. And they have, in the sense that they are not connected by wire, like the geophone. There are no cables, but they have wireless connections like your phone have, like Bluetooth connections and all that. So in the field, they just put them one. They all stand on their own. You can see this diagram showing a node. So different companies have different ways they design their nodes. Look at the second node here, designed by TGS. It looks like the normal geophone. It has a spike and a leg that is like a spike and all this, but inside it, it has the wireless connection features or features. And also this last one by Wireless Seismic, another company, is also a node. Looking at it, it look like a small box, and it has an antenna. Has an antenna attached to it. It's also a node. Sometimes when all of them are rechargeable, all your new nodes are rechargeable. At the office, they will charge all of them. Okay, and then they go to the field and deploy them, just like you deploy your geophones, but there are no wire connections. So you connect them directly into your workstation wirelessly. We all know what wireless connections are, so no need to elaborate that. So the nodes, you can see this man on the image. He's carrying something that looks like a backpack, and in this his backpack, he has multiple nodes. This is a stride staff, and then also he has his tablet in his hand. Okay, all his gear, he's carrying it, only him. What then happens? In the field, only him will lay the nodes. Maybe he will have one assistant. So 1-man or 2-man team, they will put like 30, 40, 50 nodes in one day. Okay? So it's time consuming, less expensive in terms of labor. For the geophone, you need a lot of manpower to put your geophone, a lot of people carrying the cables and all that. But here you need less manpower because there are no cables to carry. Okay. And then for the nodes, as you're acquiring the seismic data, you're seeing the seismic response or your seismic data quality. because you're connecting in real time to your workstation or your tablet or your laptop or your tablet. So you can image your data quality or your data as you're responding. You're getting them the response immediately. They are easily deployed. They don't have much SSC consigns because they are, they put them one. So you don't need to run wire and maybe cut down trees, cut down bushes while doing the installation. You have less interference with the ecosystem and all that. So that's the major advantage of the nodes, and that's why it's getting more popularity in recent time. More than the geophones. The geophones are still in use, so don't get me misunderstood. The geophones are widely still used, but nodes are making the job a little bit easier. So there are all types of acquisition receivers. Okay, this is for land. Okay, the two of them, the receivers, the geophone and the nodes are for land acquisition. So when we come to marine acquisition, when you want to acquire seismic data in the marine setting or the offshore environment, as shown in this cartoon, there are different sources and different source type is used. We don't use the dynamite or vibroseis, but for here we use the air gun in marine acquisition. The image on the far right is what an air gun looks like. Okay, these two images on the right, these are what air guns look like. And so in the marine setting, the air gun is deployed like 2 to 5 meters below the water surface. And you can deploy more than one air gun into the ground. And then these air guns, what they do is that the air gun generates pressure. They generate pressure that are transmitted that transmits into the subsurface water body. Okay, the air gun transmits into the subsurface water body, and they generate pressure of up to about 2,000 to 3,000 psi's. So the air gun are submerged some meters below the water surface, and that's it for them. And in the marine setting, it's just the air gun that is the source type. We don't have any other type of source. It's majorly the air guns. Okay. Now, when we talk about receiver in the marine setting, there are various types of receivers, and the most common one is the hydrophones. We've heard of the hydrophones. I'm sure most of us have heard of them. So what this hydrophone measures is the returning seismic pulse within the water column. Remember, in the marine setting, during acquisition, if you're using your hydrophones will be floating on the water body. And the hydrophones are, look at the image on the top part of the screen on your right. This is what the hydrophone looks like. Now, these hydrophones are put into these cables, like your PVC tubes. I know you see these PVC tubes they use for optic cables and optic lines. That's what the receiver lines will look like. They are called streamers. So during acquisition, you can hear somebody say, "Is it a lander?" If it's marine acquisition, ask you how was it acquired. He said it's streamer acquisition. Streamer in the sense that your hydrophones are enclosed within these plastic tubes, and these tubes will be floating on the ocean surface. Okay, just like you are seeing on this image, and then they will be towed by a ship. Okay, they'll be towed by a ship. Okay, so each of the receiver streamers represent your receiver lines. And so within the streamer, you now have your hydrophones placed on specific intervals within the tube. Like you have your receiver intervals whether you want the receiver interval to be 50 meters apart, or 25 meters apart, or 100 meters apart, you do that within the streamer tubes, because your hydrophones will be inside the streamer tubes. Okay, so that is it for hydrophones as marine receivers, or receivers for seismic acquisition in the marine environment. Also in the marine environment, we have another type of receiver called the ocean bottom nodes. So the OBN, called it the OBN. Just like I explained in the land nodes. In the marine setting, we have different nodes. Shown on this cartoon here, different nodes, different shapes, depending on the company that built the node. It could be small in size, it could be relatively a bit large, like a small pot and all that. So within the node, what happens in seismic node or the OBN is that they deploy this node into the ocean floor. So in the marine environment, they don't tow the node on the surface like you tow your streamers. The streamers are the most common type of marine acquisition equipment. So you're on the surface, you have your streamer like this. But here, you have the node on the ocean floor. You can see these dots, these yellow dots. These are your nodes placed at constant intervals apart. So they behave like you're doing land acquisition, but they are not actually land acquisition. They are marine acquisition. So in the offshore setting, the nodes are deployed at the deep bottom of the ocean, okay, using special equipment to go to, or special robots to go deploy these nodes in the ocean floor, okay? The only major setback with the nodes is that they don't deploy the information. You don't get your data back immediately like the land node. The land node transmits using wireless means, or like your wireless Bluetooth or whatever wireless method. But for the land nodes, after the acquisition process, they recover the nodes and start downloading the information from the nodes. So they don't do real-time monitoring in ocean nodes, because the ocean water will not allow you to transmit current so transmit data in real time and all that, except it's in very, very shallow water. But for the deep marine sections, it's quite nearly impossible. So the second type of receiver for marine setting is the nodes. The third type of receiver is the ocean bottom cable, okay? OBC, ocean bottom cables. So just like you have your land receiver lines, here in the ocean floor, you have your receiver lines placed at the bottom of the ocean, just as shown on this cartoon. Okay, you can see them a better, closer view. You place the receivers at the bottom of the ocean and still connect them by cables. So we call them the OBC. So you can get to an organization and they are talking, if their asset is in the marine setting, their block is marine setting, and they are talking about their seismic data acquisition. They say somebody like, is it OBC or OBN? So you understand what they are talking about. Let them not use terminology and bend your neck. If they say OBN, it means it's ocean bottom nodes that they use to acquire the data. If they say it's OBC, then you know it's ocean bottom cables that they are using. It means that the receivers, the hydrophones, are placed at the bottom of the ocean. If they say streamer acquisition, it means that the hydrophones are floating on the water. So each of these types of acquisition, depending on the receiver type, has its own peculiar advantage or challenge. Remember, if it's streamer that is floating on the ocean surface, when you shoot the seismic wave, the wave will have to travel through the water column before it gets to the ocean floor and starts transmitting into the subsurface, come back to this, when it reflects, this reflecting energy will come back to the ocean bottom and transmit through the ocean, the water column, and get to the receiver that is floating. That is for the streamers. So the essence of trying to do OBN, OBC is to eliminate the effect of the ocean water column during acquisition, because it will introduce some kind of noise in the seismic data. So seismic acquisition in the marine data setting has their own peculiar noise types and these noise types the water column can introduce those noise. So the advantage of the OBC is ideal for shallow water acquisition. Is usually flexible where you have your offshore equipment and platforms. If you're doing acquisition in marine environments, those they are offshore rigs. If you're doing stream acquisition, they don't acquire close to the rigs. They avoid the rigs because you can't go near the rigs and be shooting dynamite, so you don't damage any of the equipment or whatever. And the acquisition boat or ship does not come near the rig. They give a distance like some meters, like 50 meters or 100 meters away from the rig. So within the rig regions, the streamer will not pass. So they will not acquire that place. They will only interpolate that side during processing. But if you're using OBN and OBC, you can go to the ocean floor and put your data and put your receivers, irrespective of the platform floating on the ocean. That's your ocean, the offshore rigs. You can go to the ocean floor and put your receivers. OBC is much more difficult to deploy, okay? But it allows you to cover quicker coverage of areas, especially in deep water environments and all that. So this is it. This is the third type of receiver that you use for marine acquisition. Okay. We'll be ending this class here. By next week, we will not get to next week. Within the week, I'll be able to take another class within the week. Moderator, take note of that. So we'll have another class where we'll start talking about the dimensions of the seismic survey, where you talk about the 1 dimension, the 2 dimension, 3 dimension, and the 3D, 4D, and 4C seismic. So we'll talk. That will take us another 2 hours. So we'll not continue for today. So, is there any question so far? Yeah,
Yes,
go ahead.
sir. Okay, sir. Does that mean that OBN is wireless?
OBN, yes. OBN is ocean bottom nodes. When you hear the word node, okay, it means that the receiver does not have any cables connected to it. Anytime you hear node,
Okay,
you are
sir.
using a
Okay,
node.
sir.
There's no cable. So it's just a standalone equipment. So the receiver is just standing on its own. And inside it, you have all the recording equipment and all that. And it has its battery. It's just like a small gadget. It will have a battery. And it will have a storage, maybe a USB card or whatever, a hard drive inside it. So if it's on land, the node will have ability to transmit. So it will have like a Bluetooth connection or whatever type of connection where the data will be transmitted from that node to a workstation in real time. You connect it the way you're connecting your phones. But for the marine one, in the marine environment, the node, because it's at the bottom of the ocean, the ocean is very deep. You're not going to, most time they will not have a connection, but they will just deploy it. It will have a battery and a memory chip that saves the data as it's acquiring, but it will not transmit. So after acquiring, they'll go and recover the nodes and then download the data that it has saved inside it. I don't know if you get that point.
Yes, sir.
Okay.
Okay, sir. Sorry to draw you back again. Please,
Mhm.
can you recap on what you said about our CMP and CDP? I didn't really get the difference between the both of them.
Okay. My CMP simply means the distance between two the midpoint between the receiver and the source. Okay, if you have a source, the distance between the source and the receiver is a common midpoint. So if the distance between the source and the receiver is 100 meters, the CMP is 50 meters. Okay, that is for the surface. But at depth, where there is a reflection, at the point where the seismic ray path has reflected at the geologic boundary and goes back from the source to the receiver, that point where reflection occurs is now a CDP, a common depth point. It is also at the middle between the receiver and the source. So CMP is on the surface, CDP is at the subsurface. But they have the same thing, the middle distance between the receiver and the
Okay.
surface and the source. CMP is on the surface, the ground distance between the receiver and the source. But the CDP is the midpoint between the receiver and the source at depth in the subsurface. That's what it simply means. But mathematically, they are the
Okay, sir.
same.
Thank you.
Okay. Any other question?
Yes, sir.
Okay.
From what you just said, can you say that a grid is a CNP?
A grid.
Yes.
No. A grid gives you a beam, okay, which is the smallest grid that you have within your acquisition area. I'm running out of battery, so I'm going to reconnect to this through my phone. Okay. So in case if I lose connection from my if I lose connection from my laptop, I will reconnect from my phone. So I will continue the discussion and you will not see my slide again. So the grid is the smallest point of the seismic data in terms of the beam. Now, within that beam, you have that beam will serve as a CMP point. Within the beam, you have multiple CMP points for
Okay.
multiple receivers and multiple CDP points, or rather, for a particular receiver and source. I don't know if you get me.
Okay, sir.
So that's what it's actually the grid means. It's not just for one CMP. It's for multiple. It serves as one CMP, but for multiple receivers and multiple sources. So the higher the number of receivers and sources that uses that particular grid point or beam as their CMP, the higher your number of folds.
Okay, sir. Then also, sir, the short points. I don't know if you see the short points. Like when you
Anthony, please hold on. I think his
oh,
battery is down, so he would join. Okay, he's here. Hold on.
You will not see my slide again, but we have done for the day. So for pre-presentation part, I think I've exhausted the part I will take today. I'm only going to take the last of your questions if you have any.
yes, sir. I still have one question.
Yeah, go ahead.
Okay, like when you arrange your receivers, let's say for for a SWAT,
Mm.
like is it maybe you now take his like one shot after the other, like when you
Yes,
already have
yes,
okay, sir.
yes, yes. When during acquisition, let me use
Yes,
land
sir.
for instance. The receivers will be placed completely. So your receiver lines, if you have
Yes, sir.
receiver line 1 as I illustrated, all the geophones, for instance, on that receiver line will be placed and connected. Let's say we are using geophone. You place them and connect them, and they are not to be removed. All of them are already in place. And if you have 5 receiver lines, you place all the receivers on those receiver line. When you mean receiver lines, the geophones will follow a straight line. Okay, you put geophone 1, geophone 2, they will follow a straight line, and that straight line of geophones will give you what we call one receiver line. They can be 10, 20, 30, 100 geophones on one receiver line, depending on the survey density and all that, and the length of the receiver line. So you have them for receiver line 2 as well, receiver line 3, and all that and all that. All the geophones have been placed, and they are stationary, they are not moving again. Now, the short points are going to run perpendicular to the receiver lines, but they are going to be taken one by one. You don't shoot all the shots once. So the short points, short point 1, they have already drilled the short hole at that point. They put the dynamite, for instance, there, and they will shoot. When they shoot there, they wait. When you wait for a couple of minutes, what happens is that the seismic wave that is generated by that one shot will transmit into the subsurface, come back to the surface, and be recorded by all those geophones.
depending on their angles from the short point. You know, some of the geophones will be close to the short point, some will be far from the short point, but all of them will record, because you know, in our illustration we are using the seismic ray path, which is like an arrow, but in reality it's not one arrow that is being used, like is in play. The seismic wave travels through the wave front. So the wave front is not like one arrow that we use to do our cartoon illustration. The wave is traveling in ripples, okay, in a wave front away from the source. So as the wave is traveling, it's getting to the interface, reflecting and going back to the surface. Different geophones are picking back information at different times, okay, based on their offset from that short point. Please, moderator, keep this question for me. I will illustrate it with a cartoon by next class. That will be the first thing we'll take care of.
Okay, sir.
Okay. But I hope I threw a bit light to this. So during acquisition, they shoot the source one, which is your short one, and all the receivers will record it. Okay. Then they move over to short two, and they will shoot. All the receivers will record. They'll go to short three. Okay, along the receiver line. So, along the short line. You know, the short lines will run straight, perpendicular to the receiver lines or thereabout. So they shoot them short one. After short one, you go to short two. So what is changing is the short points, but the receiver points are stationary for land acquisition, especially. But the receiver points are stationary. So they keep changing the short points, and each short point will be recorded. And you know that each geophone will give you a trace. So a combination of all the traces that were generated when short one was fired rather, will give you one shot gather. So I will explain that further when I take you in a bit of acquisition. So when you shoot once, you generate a short gather, and that short gather has multiple receivers, as in information gotten from different geophones during when that one shot was fired. Then you move over and get the second shot and all that, so on and so on. Does that make sense?
Yes, sir. Yes, sir. Thank you, sir.
Okay. Okay. Any other question? Okay. Any question? Okay.
Yes, sir.
In the
I have
absence of
questions
okay.
concerning
Okay.
fold.
In the what?
Concerning the fold.
Yes, food. Go ahead.
So from the references you draw, included in the last slide,
Uh,
I checked one and they gave a formula for fold.
yeah. Formula for
They
food.
said yes,
Mm.
and they said it is the number of geophones over 2 times the spacing between the source line and the source point.
Okay.
I don't know whether
Uh,
like that was
okay.
what I interpreted to mean. So I don't know if it is correct.
Food. Food now. Uh, Practically, what a fold means, if you understood what a CDP means, a common depth point in the subsurface. Now,
Okay.
that common depth point within a bin, okay? Because you
Yes.
divide the acquisition area into small grids of bins. So each bin will act as a CDP. Now, that within that bin, you will have multiple receivers imaging that point and those multiple receivers will be at different offsets, and they are receiving from shots that are in corresponding offsets away, so that that CDP or that bin will act as a CDP, or that bin will act as a CDP or a CMP on the surface between the receiver and the shot. Now, the number of receivers that were able to image that particular point, okay, gives you the fold. The number of receivers that image a particular point will give you the fold. Moderator, also take note of this question. Note it down and send it to me as a reminder. I will add that. I will address it better in our next class before we proceed. So the fold,
Okay, so
forget about the formula they are using to calculate the fold. Just understand the basic principle behind the fold. When you hear the fold, it means that a particular, just use our ray path imaging description. It means that a particular point in the subsurface, the point which is our common depth point in the subsurface, is being imaged by multiple receivers, okay, during the acquisition. And the higher the number of receivers that particular point became a reflecting point for, the higher the number of folds. So if you have 50 receivers that a particular point in the an imaginary point in this case in the subsurface is if you have 50 receivers that used that point as their reflection point or their seed or their common depth point, that's if that means that you have 50, that data will have a 50-fold data. So the idea is that during acquisition you have more fold, meaning more receivers imaging one particular point in the subsurface. I don't know if
Okay,
that's
sir. Thank you, sir.
okay. Moderator, please put that also. I will update my slide to address this question.
all right, so
Okay. Any other one? So in the absence of any further question, I think we can call it a day. The last part of the lecture will be on dimensions of the seismic survey, where you talk about the 1D, 2D, and all that, which it is not a 1 hour talk, so we can't finish it. And also, I ran out of battery, so we'll end here. And also, third factor is fatigue, listening for the past 2 hours and all that. So we don't model up so much information. So what I would like you to do is you go back, just Google seismic folds, seismic common midpoint, fold, and beam. Read it up on your own and try to get more insights from different sources, materials you can come across in the internet. So by next week, I will throw more light on these two questions that were asked, and then we will proceed and round up. It won't be on Saturday anyway. I'll try and fix it. I'll give you a class within the week. Any other thing? Moderator, are you still there?
oh yes, I am here. Thank you very much, sir, for taking us on today's class. It was educative and very informative. Thank you so much, sir. We are really grateful.
Okay.
And
Okay.
we'll talk later to fix the class for the week. Then I would communicate with everybody on the group.
Okay. Okay.
All right. Thank you so much, everybody, for joining today's class. I'm sure it was worth your time, and we'll talk on the group. Thanks a lot. Thank you very much.
All right. Thank you, everyone.
And thank you, Emmanuel, for being there. Thank you so much. So we'll call it a day. You can stop the recording. Thank you.
All right. Okay, Messi. Thank you. Have a nice one. Bye-bye.
All right. Thank you, Emmanuel. Talk to you.